Containers became widely popular around 2013-2015, following Docker's launch in 2013 and Kubernetes introduction in 2014. We can say that if a virtual machine virtualizes hardware and runs a complete guest operating system, then a container isolates one or more processes while sharing the host operating system kernel. These processes are isolated from other processes, but their performance can still be affected by other workloads, as with virtual machines. The key difference is that containers also share the same kernel. To isolate a set of processes, we must isolate resources and system views, such as the file system, process IDs, user IDs, network interfaces, and inter-process communication endpoints. That, as an example, allows for processes in different containers to have the same process ID. We may also define limits, quotas, or priorities for memory, CPU, and input-output. To do all this, we either use namespaces or cgroups. Namespaces isolate what processes can see, while cgroups control or account for the resources they use. More concretely, if we focus on namespaces, a namespace is a kernel feature that limits or isolates what a process can see and access. A process belongs to one namespace for each type. New namespaces can be created when a process starts. As an example, I might want to start a process and associate it with a new mount namespace, so that the process gets a restricted view of the file system. For example, only a specific folder and its subfolders. In that case, I can create a new mount namespace and start the process in that namespace. A process can also join an existing namespace, of course. We do not need to create a new namespace for each new process. Nonetheless, as said before, for memory, CPU, and input-output, a namespace is not enough because we need a mechanism for the kernel to account for resource usage and enforce limits or priorities. Going back to the file system example, a mount namespace isolates the set of file system mounts visible to a process. Two processes in different mount namespaces might see different file systems or different directory trees, even though they run on the same host. Container runtimes use mount namespaces together with other file system mechanisms to give each container its own root file system. If we focus now on resources that require monitoring, what we have is that the kernel provides controllers for resource types such as CPU, memory, and input-output. For each resource, cgroups are organized in a tree and specify restrictions. A process can belong to one cgroup for each resource. For example, we could have a CPU controller with a cgroup called C1 representing a 50% CPU limit. I'm using percentages here only as a simplification. And a memory controller with a cgroup called M1 limiting usage to 2 GB. To limit processes A and B together to 50% of the CPU, we place both A and B in cgroup C1. To also limit process B to 2 GB of memory, we place B in memory cgroup M1. So why are cgroups hierarchical? Why are there multiple controllers? The hierarchy allows limits and resource distribution to be defined at several levels. Multiple controllers exist because CPU time, CPU placement, memory, input-output, and process counts require different accounting and enforcement mechanisms. In the previous example, A and B together received 50% of the CPU. To divide that allocation further, for example, 80% for A and 20% for B, we can create two child C groups below the 50% group. Note that some controllers affect aspects of execution that are related. For instance, the CPU controller manages CPU time, while the CPU set controller determines which CPUs a process may use. On a 4-core system, restricting A and B to 2 cores prevents them from using more than 2 cores simultaneously. So in a sense, that also limits A and B to maximum 50% of the CPU. Note also that different restrictions may conflict. For example, a process may belong to a CPU set C group that permits only core 1, while one of its threads is pinned to core 2. The operating system enforces the intersection of these restrictions. Since the thread has no eligible CPU, it cannot be scheduled until one of the restrictions changes. As we said, different controllers manage different resources. For example, the CPU controller manages CPU bandwidth or relative weight. CPU set controls CPU and NUMA placement. And memory controls memory usage, and PIDS limits the number of processes or tasks. The devices controller manages device access. Please note that Linux supports two main versions of the cgroup interface. In cgroup version 1, controllers can use separate hierarchies, so a process might belong to one cgroup for CPU control and another for memory control. Cgroup version 2 uses one unified hierarchy. A process belongs to one cgroup in that hierarchy, and the relevant controllers are enabled for that part of the tree. This provides a more consistent relationship between processes, parent groups, and resource limits. The following examples mix both versions because their purpose is to illustrate what cgroups can do rather than the exact configuration interface. Let's look at a more thorough example for the CPU controller. Each cgroup is assigned a number of shares. Typically, a system slice contains system services, user slice contains user processes, and machine slice contains virtual machines and containers. In this example, these three groups and G1 have equal shares. Note that shares matter only during contention because they define relative fairness, not fixed limits. Under contention, G1 therefore receives approximately 1/4 of the available CPU time. Within G1, G1.A has 1,000 shares and G1.B has 10,000. G1.A therefore receives approximately 1/11th of G1's allocation, or about 1/44, so around 2.3% of the total CPU capacity under full contention. If you want to enforce a strict max, you can do that instead with CPU.max in cgroup version 2. Different controllers use different types of thresholds. Memory limits, for example, are commonly expressed as absolute byte values. Here, G2.1 is limited to 1 GB and G2.2 to 1.5 GB. Together, however, they cannot use more than the 2 GB limit of their parent, G2. A child cgroup is constrained by both its own limit and its ancestors' limits. If you want, you can check the membership of each process. This file shows the cgroup membership of process 4042126. Each line identifies a cgroup hierarchy or controller and the path of the cgroup to which the process belongs. If you want to check the cgroup user slice for blocking input-output, then this directory contains the cgroup version 1 blocking input-output controller files for user.slice. For example, reading the highlighted file shows the accumulated bytes transferred by devices for this cgroup.